welcome to lecture 13. Today we'll cover the last really important model of this class, namely convolutional neural networks. They have been very successful in computer vision, and they actually can also be applied with some minor modifications and or simplifications to natural language processing. In fact, they're so popular, last quarter is a class entirely devoted to convolutional neural networks, or CNNs in short, to computer vision results. And so today we'll mostly only focus on natural language processing. So this is not a standard convolutional neural networks class that, you know, if that was the main topic without NLP, then we would have a very different kind of lecture today. Before we dive into the lecture material today, let's look at the midterm. We have had generally pretty good performance. There are only very few who got above the maximum performance, basically getting some bonus points, and then a large set of people sort of around, more than 2/3 or so of the actual points. So that was good. However, one thing that did worry the TAs and me a little bit was how to derive this part, which seemed to have confused a lot of people. So just want to make sure we're on the same page. It's the only sort of derivative we'll take today, but I want to make sure we're all on the same page here. So what is the definition of the norm, right? So if we just had the norm, the L2 norm of x, and x was a vector in Rn, right, then this would be square root of x1 squared plus x2 squared plus xn squared. But now we have the square of that, so we just have this simple sum, right? And what is this simple sum? Well, you can rewrite this by switching the square here and the square root as also x transpose times x, L2 norm, right? But regardless, drop the derivative here. Regardless, you know, this right here has a very simple derivative, right? x1 squared, the derivative of that, of just with respect to x1 is just 2x1, right? And so again, we can write these out for all the separate indices, and we just get 2x. So for those people who have missed that, I do encourage you, before this class is over, to really go through the various materials again. Check out the Matrix cookbook if you want to get extra sort of practice taking derivatives of matrices. The Matrix cookbook, just Google for Matrix cookbook, has a bunch of very interesting derivatives that you can take and try to write out sort of by hand, how you would do it, and then see if you can actually arrive at the same solution that is given in Matrix cookbook. All right. Fortunately, there was not that many, but for those of you who are confused by that, it's very important to be able to follow those kinds of things if you want to implement your own neural nets from scratch. All right, so overview for today. Basically, we had covered RNNs, and today you'll often see me sort of say RNN squared, because RNN is unfortunately somewhat a terminology that is ambiguous in the sense that it could be a recurrent neural network or a recursive neural network. So we'll see if we can move from RNNs to CNNs and sort of motivate CNNs a little bit. And then basically cover one of the simplest variants in a paper actually from last year or a couple of years ago. Was actually first introduced by Jason Weston, who gave a lecture here last week, and Ronan Colbert. And then we'll actually really go into all the details, the various hyperparameters, the various choices you can make for that model in a form that Yoon Kim published last year. And really evaluate it, and then look also carefully at this evaluation. So it's basically showing you what kinds of things you should really be careful about, and what kinds of things you should mention also if you were to write your class project report, your final write-up. And then we'll do a brief comparison between different models, and look at one CNN variant as well that is a little more complex. All right, so we've already covered very carefully recursive neural networks up here and recurrent neural networks. Again, recurrence is just a special type. Chain structures are just special types of trees. And so in some ways you could see this as a special case of this one. However, this one had the nice property that you can just go from left to right. You don't need a tree structure. So the recursive neural networks needed a parse tree. And that in some ways is suboptimal because now we have a separate objective function that needs to find a good parse tree, and then we only apply our neural network architecture to it. Ideally, we just take the raw input as is with some label that we want to predict. So that is something that the recurrent neural networks could do. However, they were then not able to capture specific phrases without the prefix context. So if I just want to understand or get a representation for of my birth, then it's not quite as intuitive. I'd have to sort of restart from 0 because in general in the RNN, the country here would always modify our hidden representation. And if we were to just try to classify that sentence overall based on the last representation, then for the standard recurrent neural networks, the last couple of words mattered a little too much, and you may forget the first couple of words. So of course, we then also had modifications like the gated recurrent units or LSTMs, which suffer less from these kinds of problems. So basically, the nice thing about the recursive neural networks was that we could get compositional vectors for only the grammatical phrases. So if you actually wanted to understand, how to maybe rewrite a sentence in order to change some predicted output, you would now get exactly the kind of phrase that mattered the most to have something positive. You can also interpret these nicely. If you say, I have not, and then a bunch of longer positive phrases, you see exactly where in the tree the not modifies the positivity, for instance, of the remaining phrase if you were to do sentiment analysis. In the convolutional neural networks, one of the overarching sort of ideas is, well, compositional vectors are good, but if we don't want to require a parse tree, why don't we just compute vectors for every single possible phrase? So if we have the country of my birth, why not just compute a vector for the country of my birth, the country of my birth, the country of my, and country of my birth. Right? So then, if we just computed all of those phrases and vector representations for all of them, then we wouldn't need to, parse initially. Of course, computing more such vectors might be computationally more expensive, but maybe we can have some other trade-offs in how we compute this, and we'll get to that later. But basically, the main idea here is, why not just compute phrase vectors regardless of whether this is an actual grammatical phrase? Just compute all of them, and so when you look at that, you realize it's neither linguistically nor cognitively very plausible. Like as humans, we don't compute a bunch of separate phrases and all of them. Clearly, linguists wouldn't agree that it's that useful to have the country of or country of my as a separate phrase. But you may have some gains, and we'll get to that later. So, what is convolution? You can write the general 1D discrete convolution, oftentimes used here the star, though we won't use that notation much in this lecture, basically as just the sum here of two functions where you keep modifying and shifting one of them. And so in computer vision, this is a really great way to extract features from images. And this is one sentence or one slide here, when really you could give an entire lecture on convolutional neural networks for images. So I just want to give you a very high level intuition here of what convolution does in 2D, because oftentimes we can actually have multiple dimensions too for NLP. So here's a 2D example. The yellow part that you see here moving around is what we call our filter, and the little red font here are basically the filter weights. So you have here 1, 0, 1, 0, 1, 0, 1, 0, 1. This is our filter weights. And now the operation of convolution basically just so-called convolves or shifts that filter across the image and computes basically just a simple sum of multiplications. So if our input of the very top 3x3 quadrant here is 1, 1, 1, 0, 1, 1, 0, 0, 1, then we basically multiply all the values of the filter at this stage right here and sum them up. So if you do the math here very quickly, you'll see this is exactly how you would get 4 here, by just multiplying all these numbers and summing them up. So that is really all there is to it. That is the general idea of convolution in 2 dimensions with a simple filter. Of course, those numbers will be different, and the main idea for us will be to actually try to learn what these filter weights should be. Are there any questions about what we see here? All right. So of course, we don't necessarily start with 2 dimensions in natural language processing, right? We usually have one vector representation for each word. But instead of having the RNN here compute only bigrams for my birth and the country, and later on compute longer phrase representations, what the first layer of a convolutional neural network would do is just compute a possible representation for every single bigram in the first layer. And one simple way that is the most familiar to you to do this computation is exactly the same equation that we had for recursive neural networks, where we take each child, we concatenate the 2 child vectors, apply our affine transformation, a simple matrix multiply of that, add a bias term, and apply an element-wise nonlinearity. That is the simplest first convolutional layer. So why did we call this a convolution? You can essentially see this as having vectors here, and now you apply the filter to these 2 words, and then you convolve, you shift the filter 1 to the left, and you apply it again. You shift it again, 1 to the left, or sorry, 1 to the right here, and you apply it again. Shift it again. And so basically, just reapplying this, and it turns out in this case here, you don't even need to actually shift it. You can in parallel run all this computation, right? Because running the filter here doesn't really modify what you did here. And this is actually where you can get advantages, because you can run things in parallel. All right. Does that make sense so far? Great. Okay, so now we eventually want to have a representation of the full sentence. And so we can basically, there are different options for getting there. And the very first option, which is the simplest to understand, but not necessarily the best, and we'll see variants very soon, is to just basically repeat this, but use a different set of weights. So instead of having just the first W here that allowed us to compute the bigram representations, now we'll just take a different set of weights, and we do the same thing again, which is we convolve a different set of weights over these vectors now. And we just take the same W2 here, apply it to compute this, same W2, compare this, and so on. And again, it's the same exact equation that we had before. Yes?
Yeah, would it ever make any sense to zero pad the ends?
That's a great question. Would it make sense to zero pad the ends? I'll very briefly, towards the end, define the difference between sort of a narrow and a wide convolution. For now, we'll just assume we only have the narrow convolution. We'll come to zero padding soon. Yeah, great question. All right, so basically, we noticed here already one difference, which is in the recursive neural network, we had used the same W at all the different nodes, whereas here we will only use the same W across one layer. We will basically call this layer 1 and this layer 2 here, and share the weights only inside one layer. And basically, to conclude this simple option, we basically run now with the third set of weights to compute now representations for 4 grams. So this vector here, we would assume represents all the words that went into it, namely these 4 here. And this vector here would represent these 4 words. And then we compute the top vector. So that is basically the simplest kind of convolutional neural network to compute a vector representation. Now, we did more matrix multiplications here than we did in the RNN, but one, we can parallelize them, and two, we don't need a parser. So we can train now, we can have a softmax classifier on top of this vector and just propagate down into all the phrases. Cool. All right, so that is actually not the kind of CNN most people would use. So let's walk you through very carefully all the equations for this one, which is much more practical and has shown really good results. It'll be the next couple of slides, and the majority of this lecture will be this model. Basically, what we introduce here soon will be a new type of layer, which we'll call a pooling layer. This model is based on, like I said, Colbert and Weston and Kim. In 2014, he had a very interesting short paper, Convolutional Neural Networks for Sentence Classification. OK, so let's define this model. It will actually only need one single convolutional operator or convolution in the model. We'll have, again, our word vectors. We'll call them xi, and we'll define them to be k-dimensional vectors. So these dimensions here are important, so I have to pay attention now to some of these definitions to understand all the operations. So then we will actually define the sentence as basically one very long vector. So x1, x2, this will be our operation for just concatenation. So we'll assume here these are row vectors, and we have now one very long row vector of length n times k. Right? Because we have n many word vectors, and each of them is k-dimensional. Now, we will define this notation here, I colon I plus j, to be the concatenation of all the words in the range from I to j. So if we have 1 colon 2, then it's basically just vector 1 and vector 2 concatenated. But we can also have 3 to 5 or 3 to 6 and so on. It'll just be these vectors concatenated in a long row vector. Yes?
Do you know why they did this in terms of a long row clustering and big matrix while the dimensions are like that?
So right now, yeah, we'll get to that soon. It's basically the easiest way to define the model. You can actually eventually define them as row vectors or as column vectors and just transform your various matrices and so on. But it'll eventually boil down to just transposing various things, so it could be the same.
Because then for each convolution, each dimension would be infinite if you have it lined up in terms of a 3D matrix.
Right, but you can also you can actually also have yeah, it'll boil down to the same thing. You can either transpose it now or later. But you could also convolve, and that's another variant. You can convolve over different dimensions too, right? So we'll get to that also. But yeah, so for now, what we'll do is we'll just convolve over this vector, and we'll just assume, this is just one very long vector, though when we write xi, we'll actually don't assume this is the ith element of this vector, but it is the ith beginning of that word vector. So that's important. All right, now we will define a convolutional filter to be basically a vector that is of length h times k. And this h here comes basically from defining a window size of h words. So if we want to have this kind of convolutional filter here that takes 2 words to compute a vector representation, then h would be 2. But we could also go over trigrams or 4grams and so on, and basically multiply all those together. So here, if, for instance, in this example, the simplest case, if we wanted to compute this vector right here that represents these, some combination of these 3 words, then these 3 would be the inputs. So how do we actually compute this? Basically using this equation right here. So again, note this vector, this W here is a vector. Our filter for now is just a single row vector. And we basically define our size h, again, randomly. We could have our own definition. It doesn't have to be 2 in, as in this example, it could be 3. And then we'll just basically have an inner product here between this filter W transpose times the word vectors concatenated for exactly that, starting in that position I, plus the window size minus 1. So if 3 here, we just basically concatenate these 3 windows as one long row vector and multiply the W. It's fairly straightforward. So this is basically, the definition here of a single neuron, as we've had in many other models. It just happens to be the case that we will compute this CI here for C1, C2, C3 using the exact same W in each computation. All right, so like I said, filter W is applied to all the possible windows where we concatenated those vectors. So what does that give us in the end? Well, all the possible windows of length h here would be x1 to h, 2 to h plus 1, and so on. And in some cases, we'll compute this, and in the end we get this result here, which we will call a feature map. So C will be the bolded C here will be a feature map of all the different C's that we have. So now this will be an Rn minus h plus 1 dimensional vector. And if you're very observant, you'll notice that we can compute these very easily with this definition for the first couple until we hit some that are basically getting close to the end. And then what do we do to compute the last vector with this definition here? And the answer is we'll just assume they're zero padded. Also, if we said, oh, we wanted to have windows of length 8, and now we're given a phrase that only has 4 words, then what these kinds of models will do is just zero pad. They will just assume there are a bunch of words of dimensionality k, the same dimensionality, but with all zeros. Which again is not very cognitively plausible. It's not like we internally map all our sentences to have all the same length and then add a bunch of zeros. Neither would linguists assume we have a bunch of non-existent words in every sentence. But that's what convolutional networks do. And they can get away with it because in the end, they work reasonably well to still classify various sentence inputs. All right, so that was basically the simplest definition here of a convolution. Just a bunch of inner products, one at a time, with the same weights at every location. Yes?
So does that mean that you have to zero pad every sentence in your corpus up to the length of your longest sentence?
Not necessarily up to the length of your longest sentence. You can also do pooling, which is what we'll get to right now. Basically, you would get now, that's a great question. Basically, when you think through this, right, you now have a different number of vectors here, right? So if you have a very long sentence, you get a lot more numbers C1 here than if you had a very short sentence. But in the end, if you wanted to plug this into some classifier, you want to have a fixed number of dimensions. And so there are 2 options. One is the one that I described in this model here, where we just keep going higher and higher until we have in this pyramid scheme a single vector. But what is actually even faster and even simpler is to do a so-called pooling, or have a so-called pooling layer. And this is a new important building block for when you want to eventually build your own neural network architectures. Basically, we'll call this here a max over time pooling layer. And the main idea is that we want to capture the most important activation across all the different applications that we've had. So maybe we had a 3-dimensional or 3-word vector pooling layer. So now we can compute all these different activations for these and so on. There are different definitions. Some will just start from the left. So the definition that we had here will always start from the left and just go h to the right. You can also actually zero pad words to the left. So there are different variants here. And it doesn't really matter too much. So we could have something that has all our 0 padding here if we have a 3 window to compute this one. And then, we'll just have one here, or you have multiple 0 pads here. It doesn't really matter. So let's stick to this definition that we had here. But basically, the important part here is that across all these different applications, what this will do is now just take a single number of all these possible C's, C1, C2 to Cn minus H plus 1, and just take the maximum value across all of them. Very simple operation. So we'll define C hat here as just the maximum number in this vector. And we'll call that pooling. We're pooling all these numbers down to only a single one. Yes?
Two questions. First, is there a reason that the end of the sentence is particularly special? It seems like it would be useful for me to take into account the same essentially 0 padding at the beginning of the sentence as well.
Take into account the same 0 padding.
On the previous slide, we think it's useful to include features that are derived from only the combination of the last word and some 0 pads. And it seems it would make sense to do that for the first word as well.
Well, like I said, you can have different definitions. It turns out to not matter that much overall. You're basically going to capture, you want to mostly capture all the various n-grams. You want to capture, some really important words by themselves. So you could even have a convolution with, a single window and then pool over that. You want to capture the bigrams and the trigrams and the fourgrams, and those will be captured in both of these, right? You'll have here the first trigram and, the third to last computation, you'll have the last trigram. So it turns out to not matter that much.
And my other question was just the max and max pooling is done element-wise overall?
That's a great question, yes. So this is, in some ways, just like our nonlinearities, it is element-wise. That is, sorry, no, this is actually vector-wise. So like, you look for each element, you find the largest one, and then you just get a single number out. So this max here is literally just a single number. We've so far only defined a single neuron output. Yeah, it's a great question. Yeah, this is, you look at all the elements and then you find the largest one. Maybe, let's say, for instance, you have sentiment analysis and you say, this movie was really awesome. And you look at all the bigrams, and basically you would hope that after training our weights W here, which we'll use again, same sort of backpropagation kinds of algorithms that we had before, we would hope that very awesome has the largest activation for the filter that tries to find positive words. And then we just take that single number. And this leads us to probably the exact question that you had here. Obviously you want more features than just a single one. And so eventually we can actually have various matrices and have multiple filters, and then eventually this will be element-wise. But in this definition right here, so far, we've only defined a single filter, and hence we only get a single output. So how do we actually make this model more powerful and allow it to capture different kinds of filters and different kinds of features? Basically, the main idea is we'll just have a whole set of these W's. So instead of having only a single W vector, we'll have a bunch of them. And this is also when it now kicks in that you can actually do matrix multiplications across your different vectors to get different elements. And so, however, because we have our max pooling, the length of the actual C that we have here is irrelevant. So we'll have, if we have 10 different W filters, we'll have, in the end, exactly 10 bolded C's, right? And even if one filter is, a two-dimensional filter, so one filter may only go, over these, and another one might go over all three, and so on. In the end, we'll still look at the maximum value that we had here for all the C's. So this will get us one C1, and this will have 1C2 hat. All right, so that's basically it. This is a convolutional neural network for you for NLP. Yes?
So it seems like this type of max pooling layer is throwing away all of the location information.
Sorry, say again?
It seems like the max pooling layer is getting rid of all the location information
Yep.
in the sentence. So like if you have in your example, this movie's really good, you want to actually know that it really comes before the word good. And it seems like that might be like relevant for doing sentence analysis.
So it's a great question. The question is, basically this max pooling operator loses the locality of where our features actually happened. And it was almost right in that it does lose the locality of the n-grams that the filters of length n times the word vector k actually have. However, you still get the really great or really awesome or whatever being a bigram, and that bigram has its own filter. So all the bigrams have a filter, all the trigrams may have their own filter, and then you can still capture various different things with those. So, but you lose the location of where those trigrams were.
Sure. So if you rearrange the sentence like sort of randomly, but I guess you have to maintain like the n-gram order.
And you can't really maintain them because the n-grams keep overlapping a little bit, and so it'd have to be quite complex to try to get the exact same representation. Yeah, it's good thinking through the model. Yeah. All right, so like I said, we'll have not just a single W for specific window length, but we'll actually have multiple. So we can have one that looks at 2 words, a filter, and then have another 100 such filters that all only look at bigrams. So, and then we have another 100 that look only at trigrams. And we basically just concatenate all their numbers, all the C's that we get to get one final vector representation that is now always of the same length. So this is basically a convolution plus pooling layer for a single sentence. So now in the paper by Kim, we actually also have a couple of extra tricks, and one is so-called multi-channel idea. The sort of phrasing of multi-channel comes from computer vision, where you have RGB channels, and for us the channels will be basically, we'll start at 2 copies of word vectors. We'll again initialize them with word2vec or glove, what you've learned in the first part of this class, and then we'll actually take derivatives, but only with respect to the word vectors of one of the 2 channels and not the other one. So the first channel basically has the word vectors fixed and they won't ever change, and the second channel lets them change, and then we will basically pool over them both separately with the same filters, and in the end just sum up the 2 activations C1 that are in C1, C2, C3 and so on before we do the max pooling. So basically now one of the filters can push through to the word vectors, and in one of these channels now basically modify the word vectors. So if you train for sentiment, for instance, you can now push good and bad far away from each other, whereas as we've learned in local contexts, sometimes antonyms actually have similar vector representations, and so good and bad may start out being quite similar, and then if you train with sentiment, you can push them away in one of the 2 channels. Does that make sense? Yes.
You duplicate it 3 times and have like 3 channels and then maintain more ways. You could maybe like learn more definitions, I guess.
You could earn. What would you want to do with the third channel?
Well, like earlier, like at the beginning of the class, we talked about words in the dictionary which can have like multiple meanings, right?
Right.
Like the same, homonyms or something.
Yeah.
I don't know. I mean, maybe those are like a tiny minority of words actually, but you might want to learn multiple meanings.
Yeah, that's actually a good idea. Could we have multiple channels? And we absolutely could. You could in fact have different word vectors. We take some from glove, some from word2vec, some from another model, and you have multiple different channels. And you can decide whether you want to backprop into some of them or not. That would definitely be a reasonable extension. And then you just convolve with the same inner products over all of them, and then you add the activations from each of the filters and then still do the same max pooling. Yeah. Yeah.
So why do you simply add them? Do you need to put some weight?
It turns out that you could learn an extra weight here, but you could also, this is just in our product, right? So that weight could also just get multiplied into the word vectors or the filters, and then you'd get something very similar. So it's just linear transformation. It's like it's kind of stacking multiple linear layers up, but you still only have a linear layer in the end that could be combined into one matrix. Cool. All right. So that was basically our first convolution, followed by one max pooling layer. And that gave us the final vector of a bunch of C1s to CMs, assuming we have M filters. And again, those filters could have various different window lengths. So the first set of 100 filters goes over bigrams, next set of 100 filters goes over trigrams, and so on. So now once we have our final feature vector Z here, we'll basically just apply a softmax layer that we already know, and we can get our final output. And now if you wanted to do the math here, you would basically, the only thing you would have to remember is which one was the maximum value, because all the other ones in your set of C's were basically 0. So you only backpropagate to the one that actually had the highest activation. But other than that, it's the same kind of backpropagation algorithm that we've covered in all its gory details before. So to help you be able to read the literature, here's the original picture from Yoon Kim's paper from last year, where we basically have a sentence here: wait for the video and don't rent it. And basically here we have our n by k representation of the sentence, where we assume here we have one non-static channel. He calls the static channel being the word vectors that stay where they are from the initialization, and the non-static one is where you actually backpropagate into the word vectors. And so we have here n words, and again we possibly zero pad them if we have a very short phrase that doesn't even have n of them. And then each word basically has k dimensions, so we have here k columns. And then we have different filters. So the first one here is 1, 2, 3, 4, 5, 6, 7 times. We can apply here a bigram filter that basically multiplies all the elements in these two rows and sums them up to give us this number. And we could have a different channel here, the one in the back, where we have a trigram filter, and we multiply all the weights here, sum them up, take the max, sum them up here, and then we get basically this activation at this area. And then all these different filters, so this trigram filter here only has 6 instead of 7 different elements that it computes for your CIs, but in the end you just take the maximum value across all of them to get your max pooling over time layer. And now that's fixed size, and you plug it into your softmax. All right, so if you just do this model, it works reasonably well, but not quite as well as a couple of other models that we've discussed in the class so far already. And so we'll have two important tricks that Yoon used here that have since come out. And the first one is dropout, which we had already covered very briefly, but it was really very short, so we'll go over it again in a little more detail here. So basically the main idea is to randomly mask, or so-called dropout, or basically just set to 0 some of the features in our final weight vector here, or hidden dimension Z. And the way we do this is we'll basically create a very simple mask of a bunch of random Bernoulli variables, R, and they basically have a probability P of being 1. So the higher P is, the more likely that single number will be 1, and if P is very small, and this is basically a hyperparameter that we set, we will just delete a couple of our features Z. So it's as if nothing here happened, and this vector had all zeros and no activation. We just basically destroy the information of each of these elements in Z. We can write this here as this simple element-wise Hadamard product, where we basically have our vector here R. It's a bunch of binary numbers, zeros and ones, and we basically delete some of our features Z. So why do we do this? Basically, it prevents co-adaptation. If the model is very powerful, right, we could have a deep neural network here, but even for softmax, it could basically learn to see very specific feature constellations. Like only if I see exactly these 3 words that resulted in this number, and these 3 words here that resulted in this number, will I have exactly this combination. So this way will basically, is much more likely to overfit. And if you delete some of them, the model can't really overfit that well to the data. And then, of course, at test time, we wouldn't want to delete some of our features. We want to use all of them at test time. So this is basically only during the training time, the training procedure, such that we actually delete some of them. And then, of course, also only backpropagate through those elements of Z where the mask Ri was 1. And then at test time, there's no dropout, so we use, of course, all our features. And so our feature vector Z is larger, and the way we'll basically deal with this is just scaling the final vector, or in our case here, a matrix if we have multiple classes, by, again, those Bernoulli probabilities. So that way, that vector becomes smaller, and now you basically have all the features in your test example. And what's kind of amazing here is that with that simply deleting some of the features sometimes, Kim actually reports a 2 to 4% improved accuracy across the various different data sets. So on every data set, it gave at least a 2% improvement up to 4%. And this is going to be kind of important when we critically look at the comparison of this paper with other older papers that we've covered in the class. What's also great is he actually is then able to use much larger weights. So he can now have, instead of having only 10 of our different W weights, he can actually have 300. But he doesn't allow any of them to overfit too strongly, and still gets them to basically capture different kinds of features for different kinds of inputs. So very important, dropout. It's a great trick. Another one that he uses, which is somewhat less common, is to actually constrain the L2 norm of all the rows in our softmax matrix. So basically, each class's row vector, he basically constrains to have a norm of at most S. So if during optimization, the norm of any of the rows gets to be larger than S, he just basically rescales it to be exactly at most S. So this will also basically prevent any of the single class weights in the final softmax to blow up. All right, so what are all the hyperparameters of the model that we've now looked at? And what are they actually set to in the paper? The way we'll find out what the best values are here is, and he reports this as having properly done this. Basically, you finding the hyperparameters using a def set. So you run a bunch of optimizations, a bunch of trainings, and then test on a development split of your data set, which is also something you should do, and you definitely lose points if in your final write-up it's very obvious you just ran your hyperparameter search on the final test set that you report your numbers on. And based on that, running a bunch of experiments on his development set, he found the following hyperparameters to be very useful. So the nonlinearity will be the rectified linear unit. Again, that's just max 0x. Then the window filter sizes he used were 3, 4, and 5 grams, which is kind of interesting. He doesn't even use bigrams, which is the really great kind of bigram. And 5 grams is only something that you could use on small data sets because we have these continuous word vector representations. If we had these discrete kinds of single numbers, single indices for words, 5 grams for the kinds of small data sets that we have here would totally overfit. Then each of the filters W that we described basically has 100 different feature maps. So you have 100 W weights for trigrams, you have 100 for 4 grams, and you have 100 for 5 grams. So you have a total of 300 W vectors that you convolve over your input. Then dropout probability is 0.5. So with 0.5 probability, he will basically delete any feature Z during training. And then we'll have mini batch sizes of 50, so 50 examples per update, which is also something we've covered. If some of this terminology doesn't make sense, you should go back through the class, because in theory we've defined all these different kinds of things, some in previous lectures and some today. And then in terms of word vectors, he basically uses pre-trained word-to-vec vectors of dimensionality 300. And this is another neat trick that you can always do when you do non-convex optimization. I think we've covered it before also. The main idea being that since the final, after running it for 100 iterations, you let your model run on your laptop or on a server for a couple of days, you could just take the final weights that you get. However, because it's a non-convex optimization, if this was your accuracy, for instance, and you ran it on a test set, you might actually see that sometimes some mini batch may have been just the right mini batch for pushing the model weights into the right direction, or after the non-convex dynamics basically end up in a really good spot. So what you end up wanting to do, and which is what he did too correctly, is to basically use your development set, and every half hour, or every one epoch, or every 100 iterations, or whatever you want to set, and it kind of depends on how large your development split is. If your development split is very, very large and it takes an hour to run that, the testing to get your def set accuracy, you don't want to do it that often. If you have a smaller development split, you can do it more often. And then after basically some amount of time, you can look at, all right, at my 500th iteration, I actually had the highest def set performance, so I keep those weights instead of taking the one at the very end of my optimization. Can you raise your hand if this makes sense? All right, great. All right, so now looking at some of the numbers of this model compared to a lot of other models, several of which we already covered in the class, like the recursive ones here, and a couple of other baselines and other models that you may have heard of from other machine learning classes, like conditional random fields. Basically, he gets really, really good performance across a lot of different data sets. So here we have, for each column, we have a different data set. And he, in some cases, outperforms these other models, like recursive ones, by a couple of percentage points. What's also interesting is, unfortunately, it's not a very clean story to use this multi-channel idea. In some cases, multi-channels get the best performance, but in other cases, the performance actually drops. So sometimes it makes sense to just have one set of word vectors propagate into those. Sometimes for this data set here, it actually made sense to just keep the word vectors fixed as is. My hunch is that the larger the data set, the more it would help to back propagate into the word vectors. And MPQA is actually one of the smaller data sets here, so you don't want to back propagate, because then you push away your word vectors again from where they started, and you generalize words to words that used to be very similar. This is something we covered in one of the previous lectures. Yeah?
So I have two questions. I guess the first one is how big are the relative data sets, or I guess order of magnitude.
Usually they have around 10,000 training sentences or documents. They're all, some are, 12, 15,000, others are like 6,000.
My other question would be...
They also vary a lot in length. So MPQA is actually a lot of shorter phrases, whereas the Stanford Sentiment Tree Bank here is a data set that we've used in the class already, so this is mostly sentences, and then I think the Trek one is mostly larger documents.
Has anybody looked at training a network for a larger data set and then maybe using the word vector representations from that to train another one on a different data set, like a smaller one, without...
Sorry, your question is, has anybody tried running this on...
There's a sort of idea in vision-related comments where you can borrow the weights.
Oh, right. So the question is have people tried to do transfer learning in some ways? So you train your various weights on one data set, and then you actually run it on a different data set, but you initialized the optimization procedure with the weights from the previous data set. And the answer for convolutional neural networks is, I think, no. But I definitely had a couple of papers and many experiments where I used the weights from one model. So the Stanford Sentiment Tree Bank, for instance, is very nice because it gives you this phrase level, labeling and annotation. And so using the weights from that model and then initializing those for other kinds of sentiment tasks works really well. And in fact, I have a paper last year at a NIPS workshop with a PhD student, her name is Hima Bindu, where we actually analyze transfer learning abilities in recursive neural networks, where we have like beer reviews and movie reviews. I think there's some like technical reviews too, like maybe it was movies and books or something like that. And you can see that the more similar the domain is in the text that you train it on, the more transferring the weights helps for another task. And so unfortunately, there is no sort of image net for NLP. It's actually something I've been thinking about a lot, sort of what would be the equivalent of the amazing ImageNet results for NLP. And the problem is that in NLP, there are a lot of subcommunities, and they don't necessarily care about each other's work as much. So the machine translation community doesn't really look that much at what parsing folks do, who don't really care about what sentiment analysis researchers do, and so on. And so there isn't really that one task in NLP that kind of rules them all. Side note. All right. Yes?
Does this model work well with full text instead of sentences?
Yeah, so it turns out that the longer your document is, in many ways, the less the actual word order matters either. Oftentimes, if you have a whole document, you kind of want to just classify, the topic. Is this about sports or politics? And then, is it like very much a good throw, or is it, a Republican versus a Democratic kind of statement or something like that? It doesn't in the end matter that much because the terms and bigrams, usually up to bigrams, are enough to tell you what the overall topic is of the entire document. So I think this model will probably do pretty well on that too, because it just captures what are the most important 10 bigrams and the most important maybe 15 trigrams, and then it just kind of sums them all up. And I think that will actually be enough. So there's a good chance that this would work well on larger documents as well. But nobody has really, you can kind of see, I think here the trek. So I think one of these data sets, I guess, actually it's interesting. He doesn't actually run it on the largest data set or the one that has the largest documents. It's called the IMDb data set from Andrew Moss, who will actually give a guest lecture next week too on speech recognition. But one of his papers before he got into speech was sentiment analysis on very large documents from IMDb, like large movie reviews. And there, deep learning actually has a hard time beating some of the simpler baselines. And interestingly enough, he also didn't run on that very large data set, so who knows? We don't know if he ran it and didn't work well, or he didn't run it. My hunch is the larger the documents, the less deep learning has yet really made a huge impact on classifying correctly what you see. Just because it is really simple. You see certain words, sports, basketball, politics, voting, election, and you kind of get it right. And then there are a bunch where you have label noise and so on. So, yeah.
So for the multi-channel CNN, does every word have multiple word embeddings?
Yes, every word has 2 word embeddings. They start out being exactly the same, but then you backpropagate into one of the channels, and then they deviate.
So fix one, and change the other one.
That is correct.
Then does the convolution become 2D convolution, or still 1D?
So you can still see it as it's the same filter, right? And so you can kind of see that it's basically equivalent, right? It's you can have the same filter copied twice and convolve over it, or you do it one at a time and then you sum them up. It becomes.
So the same W applies to.
It's the same W that is applied to both channels. Yes. Mm-hmm.
Was there like a word frequency cutoff for the model that you did your CBD room fluctuation or stop words or anything like that?
So he did not have a word frequency cutoff, but if he had an unseen word that wasn't in word2vec, he just initialized it with small random numbers such that the variance of the initialization is roughly similar to the variance of the rest of the known word vectors. So you basically just initialize new word vectors for every new word that he sees, which is also a subtle but important difference to a lot of prior work, which is said it's an unknown word. and we don't have it if we don't have it in the original set? Good question. All right, from the questions I see that people are actually starting to think about these models more, which is great. I guess you hopefully have all started to work on your problem set, the final project. So, milestone is due tonight too. And you get bonus points if you run on the right data set that you use for the end too, and you already run some baselines. So. All right. All right, so let's try to be a little critical here and see what the problem was with this comparison. So in the paper, it is mentioned that dropout gives 2 to 4% accuracy improvements. And dropout was invented and sort of popularized in late 2012. So the various papers from 2011, 2012 basically didn't have that ability. And so if you now add 2 to 4% to several of these numbers, you will then have to question, well, is the model actually better, or do we just have better optimization techniques now? Right? And this is something that you should also be very careful about. When you run something, you want to tend to optimize only your model, and one, it takes a lot of time to implement baseline models, and two, it takes a lot of time and computational resources to tune them properly as well. But if you find that something works incredibly well, in your model, you should probably apply that same trick or optimization improvement to your baselines to make sure that your model is actually indeed a better model versus you just spend more time and use more tricks to optimize it. That being said, obviously this is still a really cool result, right? We didn't need parse trees. Is very quick. You can parallelize a lot of the convolutions, and what becomes kind of a cognitively and linguistically implausible and so not nice property of the models, namely the zero padding, is something that helps you a lot when you want to run this kind of model on GPU. We'll hopefully cover that next week, but GPUs are very good at doing the exact same matrix multiplication in parallel many times. And so if everything is exactly the same size and it's the exact same kind of computation, you can use 5,000 cores of a GPU to do that kind of computation. And this kind of CNN model has that ability, right? And if the words, the phrases or sentences are too short, you just kind of zero pad them. They're all nicely in the end in the same size. Your batches all have the same size, and you can very efficiently pipe those through generally multi-core architectures. Even on CPUs, this is something that benefits you because you don't need to have a bunch of branches in your code. So the difference here to the window and RNN architectures that we described is basically that they use dropout, and they also had many filters. And so when you think about this, in all our RNN models, what we had written is basically using only a single weight W. So in our main equation, we always computed a parent vector P from two children as f of W, child 1, child 2, plus P. And we use the exact same W here at every single node of the tree. Now, the nice thing of convolutional neural networks is that in that sort of model family, that was nobody ever tried just using a single filter. Why would you? You can, in images, you might want to have one filter that finds edges of this kind, others that finds edges of these kinds, and so on. You might want to have one filter that fires for different colors, and so on. So it's very natural for images to have used multiple filters, and this is something that helped convolutional architectures a lot too. But again, we can think of trying to apply that idea of having multiple filters also to recursive or recurrent architectures. In some ways, you can see the LSTM model, for instance, that we've had as having multiple different filters also, multiple different W matrices as you go over time. Of course, they also were connected in various different ways with the gating mechanisms and so on, but you get the idea. And so there's actually nobody has explored that in recursive neural networks for language. I had one paper 3 years ago where I basically showed the differences between convolutional and recursive neural networks, but it was on 3D object classification. So not going into that model because it has nothing to do with NLP. But basically, those two ideas of having many filters and using dropout can be used also in recurrent and recursive neural networks, and it's actually something that hasn't been explored very much for NLP. So if you're looking to explore an interesting new model, this could actually be something for your class project. One thing that's also interesting, and so I think the word is still out, what kinds of models are the best. The tree LSTM model that Kai Sheng and Chris Manning had published and will come out at ACL later this year actually obtains even better performance on some of the sentence data sets that we had here, namely the Stanford Sentiment Tree Bank. So the word is still out sort of which one is the best model. I think probably next year when we get the same lecture, there will be some new interesting updates. So let's look at a little bit of a comparison here between a CNN and an RNN in the last couple of minutes. Basically, this is the kind of graph that we could see with the simplest CNN, the one I described in the very beginning. And of course, if we ignored in the second part, or well, thinking about the second part, you basically just ignored those last 3 layers here and you just pooled over the first one and that was it. But assuming we have this simple architecture, the main difference between the CNN and the RNN in terms of the architecture here is basically just those 3 extra layers that you have in the CNN. And so in the RNN, you just basically don't compute those if this was your tree structure. And what you notice here is that you can actually recover one model. You can sort of smoothly transition between having a CNN type model and having an RNN type model. So what are the transitions between those 2 models? The first one is the so-called stride size. So what is the stride size? Basically, in your filters, let's say you have multiple words and you have a filter here that is a 3 word vector filter. Now, if you have a stride size of 1, you would just move it 1 over, right? For each one, you move it 1 over. If you have, however, a stride size of 2, you would actually move it 2 over and then only look at this, right? And so the nice thing here is you notice if you basically have the stride size being as wide as your filter size, namely you have a 2-dimensional filter, then if you just have the length of that minus 1 and you go to the next one, the 2 models start looking very similar. So the stride size basically for RNNs is such that the filters never overlap. So that's one change. And then you can kind of see the RNN combination to compute the parent vector as a type of weighted average pooling, where you actually multiply the 2 vectors to get your parent vector instead of just taking the maximum value across different dimensions. And then another one that you can also actually somewhat more smoothly interpolate in between is the different models or different ways of sharing your weights of the filters. So in the CNN, we had the same set of filters for this layer, a different set of filters for this layer, a different set of filters for this layer. Whereas in the RNN, we have the same one in across the layers and across the different depths and location. And everywhere, it's basically the same set of W. Now, the other difference that I described was that in the CNN, we have basically multiple filters, and we have also this additional layer type of max pooling. And of course, the other major difference is that oftentimes for RNNs, we actually use an input-specific tree. We use a grammatical tree structure that will compute vector representations only for those phrases that we could easily replace and that are actually grammatical, whereas the CNN just computes phrase vectors for every single phrase. But it is also something that we don't have to do. We could just have a very balanced tree, and no matter what sentence you have, you use the same tree structure for all of them. And you could even 0-pad it, right? In fact, you could make this kind of CNN somewhat recursive by just not sharing the weights only inside one layer, but also between the different layers, and use the same W here, here, and here. And then you'd have a recursive convolutional neural network. So basically, you don't want to be too religious about any of these choices. And if you really want to learn about these models and gain intuition, you can actually try multiple different variants of them. And talking about variants, here's another convolutional neural network variant that actually came out before the simpler one I just described, but turns out it was actually compared to, in this comparison here, This is this model right here, and it actually didn't do quite as well, though it's not clear if they all use the same optimization, so you have to take that with a grain of salt. So we'll cover it, but not in as much detail. Basically, what's interesting here in this paper, it's definitely a nice paper to read by Nell Kaltsprenner and Phil Blunsum and Edward Gravenstetter from mostly Oxford, is basically a different type of complex pooling schemes where they try to keep around some of the location. They don't just do max pooling over all of time, but actually try to keep some location of certain bigrams and trigrams and sort of combinations of weights and not just single numbers. And they don't just do one convolution, but they actually do multiple convolutions. And there's also a previous question, I think from over there, from you, where you asked, like, could you convolve over different word vectors also and different dimensions? And this is also something they explore. So here, they start with having multiple weights, but they actually do a wide convolution. So they have, they end up with C's that have actually more C's than there are inputs. So far we've mostly described sort of narrow types of convolution. And then you can basically pool in various different ways. And then after you pool locally, you can now convolve again over those pooled inputs and so on. You can do that actually multiple times. And it turns out in computer vision, you might want to do that 20 times. You convolve over some inputs, and then you take the maximum value only in one of the ranges and one of the blocks of your original input, and then you convolve again. You keep doing that many, many times. And you can then also actually convolve across different dimensions. There are lots of options, basically. That's the number one takeaway message here. And sometimes they work better, but really it turns out for a lot of sort of general sentence classification, the simple single pooling, single convolution with one pooling layer actually worked well enough, and if you optimize it well, even better than this more complex architecture. What they had actually tried to use these kinds of convolutional neural networks for was also machine translation. In fact, this was one of the first successful neural machine translation efforts where they used this convolutional neural network for encoding and then used a recurrent neural network for decoding. So we had this kind of task already when we looked at LSTMs in the previous lecture, where we just had one LSTM for encoding and the same kind of LSTM for decoding. The very first model of this kind of neural network family for machine translation was actually, that was successful and run on a reasonably large corpus, is this one, where here we have a convolutional sentence model. They call it CSM. It's really just a standard convolutional neural network, the way we described it in the beginning. And then they condition a recurrent neural network to basically generate the output sentence. And we also already looked at this generation, and basically here you had your softmax for all the different outputs of the different language. Are there any questions about this more complex model, modulo some of the details? Mm-hmm.
Why do you use CN for encoding?
Why do you use what for encoding?
CN
for encoding? So there are some nice reasons for it, and this is actually just one of the models. There's another one where they then have a decoder that basically opens up and has a large dimensional vectors. Why do you use this one versus a recurrent neural network is your question. In some ways, you should really try both and see what worked best. And in their case, that's the model they tried, and it worked really well for them. I think that was largely because in 2013, just 2 years ago, LSTMs weren't quite as popular yet. And if you just used a standard recurrent neural network, you couldn't do very well in the translation because the last vector will have basically forgotten a lot of the previous, like the first words of the sentence. Whereas now, if you have a very large and deep LSTM, because of the gates that we described in that lecture, you can actually keep around longer term dependencies, and you can remember what kinds of words were in the beginning of the sentence. So then you can actually do that. So I think back then in 2013, while LSTMs had already been invented, they weren't very popular yet. They had probably just tried recurrent neural networks for encoding, didn't work well, and used then CNNs. All right, so let's finish the last couple of minutes with a quick model comparison of the various models that we've looked at so far. Basically, we started with a very simple bag of words, and hence for deep learning, bag of vectors model, which actually turns out to work surprisingly well for a lot of simple classification problems. You just literally take all your vectors, you sum them up or you average them, and especially if you put another couple of standard neural network layers on top of that, it actually works incredibly well. I made that observation early last year, and you get minus like maybe 1 or 2% of some of these numbers in the last table we showed with just that model. The larger the documents, again, the less useful it is to have various complex n-gram structures and so on. I think a friend of mine will actually have a paper, at least I have only seen the title, but it looks like there will be a paper out soon that runs a lot of comparisons with this simple bag of vectors model. Then we've also covered the window model, which was really good for single word classification, but only for those kinds of classification problems where you didn't need a wide context. So if you just have part of speech tagging and you only need to know the 2 words to the left, 2 words to the right, then our window model worked really well. Now, convolutional neural networks, as we've seen in the table, are very good for classification of sentences and documents. It is a little unclear how to incorporate in that model different phrase level annotations. So when they, for instance, ran on the Stanford Sentiment Tree Bank and they tried to get phrase levels and those labels, they just assumed every phrase is an independent sentence. You zero pad all of them, and you redo a lot of computation to get all the subphrases labeled for one sentence. So you need the zero padding, which also makes it a little harder to interpret some of the units. In general, once you pool, you don't really know where exactly which word had what effect on the other words. In fact, by the definition of the pooling layer, you will only care about the maximum activation, right? You will ignore all the other words. However, they are very easy to parallelize on a GPU. So sometimes even doing 10x the computation, but actually being able to parallelize very nicely still gives you more speed, which is always good. Yeah.
Recursive neural network and the recurrent neural network are to parallelize?
It's possible to parallelize them, but it's a lot more work. If you can set your convolutional operator. So one convolution is something that is implemented on a very low level on GPUs because it's an image processing kind of problem, which is what GPUs are very good at. And so they're very good low-level primitives for convolution. So if you give a very large convolution problem, sort of committed to a GPU, then it will parallelize across all its cores to do that computation, and you don't need to go into too many details of the actual GPU to make that work very well. On recursive, there are those models they're not certainly popular in image processing, and so it's much harder to do it. It's possible. I've a friend of mine did that, and he got speed ups, but it's a lot of work. All right, and then recursive neural networks are sort of the most linguistically plausible models that we've covered in the class. However, and they're nice to interpret, but you need the parse trees, and that is, in many ways suboptimal because ideally in the deep learning world, you would want to take your final output that you want to predict, the raw input, and just do everything else in a learned fashion and learn all the intermediate representations. And then recurrent neural networks, I think, are probably in many ways the most cognitively plausible models, right? We read from left to right. We keep around some hidden state as we hear information. They're not usually the ones with the highest classification performance yet, but I think there are a lot of improvements going on right now with the various gated architectures that we've covered in the class. All right, next week we'll just cover a little bit of speech recognition and look at this efficient implementation and efficient implementation details on GPUs.